welcome to the Deep Dive. Today we're looking at something really revolutionary emerging from CERN. It's an idea that could genuinely reshape how we listen for gravitational waves.
Those whispers from the universe.
Exactly. We've had these incredible, kilometer-scale laser setups for decades. Feats of engineering.
Absolutely. That's LIGO, measuring shifts smaller than a proton. Truly amazing stuff.
But these sources we have point to something different, a magnetic approach.
Precisely. Led by Valerie Domty's group at CERN. It's not just an add-on to laser interferometry. It could be, well, a whole new way of doing things. We've got some great material here to unpack.
Okay, let's get into it. The core concept, using DC magnetic fields themselves as sensors for space-time. How does that work? Turning a ripple in space-time into a signal.
Well, it's a really clever bit of physics. So imagine a gravitational wave passing through a very strong magnet.
Okay.
It actually it couples with the conducting wires generating that field.
Right.
This coupling makes the wires vibrate, just tiny, tiny mechanical oscillations. And here's the neat part. Vibrating wires inside that powerful magnetic field generate their own electrical current, an AC current that you can measure.
So the gravitational wave causes a vibration, and the vibration becomes electricity.
Basically, yes. It translates the gravitational ripple directly into an electrical signal, like the magnet is sort of hearing the wave as an electrical hum.
That makes sense. Is this idea completely out of the blue, or does it build on older concepts?
That's a good question. It's not entirely new. The sources mention it's inspired by Joseph Weber's work back in the 1960s.
Weber bars, right, those big resonant cylinders.
Exactly. The team even calls their setup a magnetic Weber bar. Here, the magnet and its electrical circuit together act like that resonant detector.
Okay.
But the key difference, and it's a big one, is tunability. By adjusting both the mechanical properties and the electromagnetic resonances in the circuit, they can fine-tune the detector for specific frequencies, potentially achieving a really exceptional sensitivity, much more flexible than Weber's solid bars.
That flexibility sounds crucial. So what new science could this open up? Where does it fit compared to, say, LIGO?
Well, that's where it gets really interesting. LIGO and similar detectors are fantastic, but they excel in certain frequency bands, mostly higher frequencies.
Right.
These magnetic detectors, because their sensitivity depends on those tunable resonant frequencies, they could be optimized for low frequencies.
Frequencies that current detectors struggle with.
Exactly. This could be our window onto things like intermediate mass black hole mergers, the sort of missing link black holes.
Okay.
Or maybe even probe exotic cosmological sources like gravitational waves from the very early universe. It really broadens the spectrum we can observe.
And the sources highlighted something particularly intriguing, this dual-purpose payoff. Can you explain that? Using magnets for more than one thing?
Yes, this is a really efficient angle. There are already experiments out there like ADMX or DM radio.
Hunting for axion dark matter, right?
Yeah.
Using strong magnets.
Precisely. They use powerful magnets, often cryogenically cooled, for that search. The idea here is, why not use those same magnetic systems to also listen for gravitational waves?
I see.
Right.
So integrate the detection methods.
Right. You run two cutting-edge experiments essentially for the price of one hardware setup. That same coil looking for hypothetical axions could simultaneously detect ripples from colliding neutron stars.
Wow, that's really smart resource management.
It's potentially a huge boost in scientific return on investment for these complex, expensive facilities.
Okay, the theory sounds incredibly promising. But what about actually building this? What are the hurdles? The sources must mention challenges, right?
Absolutely. The theory is solid, but the practical side is non-trivial. They need to build prototypes first, benchtop versions.
Test it out, small scale.
Yeah, and meticulously calibrate those resonances. A huge challenge will be noise. You're looking for an incredibly faint signal amidst all sorts of environmental magnetic interference.
So shielding and super-sensitive electronics.
Definitely. Advanced readout systems, probably sticking with those cryogenic temperatures to reduce thermal noise, and very robust magnetic shielding. It's a serious engineering challenge to reach the predicted sensitivities.
It really sounds like a convergence point, though, connecting gravitational waves and dark matter research in one instrument.
It really is. It shows how progress in one area, like magnet technology for dark matter, can suddenly open doors in a completely different field like gravitational wave astronomy.
So the big question then, could these magnetic detectors actually redefine our gravitational wave observatories in the future?
And will that synergy, with the dark matter searches really pay off and accelerate discovery? Or will the practical engineering hurdles slow things down? That's certainly something interesting for you to think about as we wrap up this deep dive.